Okay, today we'll start the chapter Applications of Differential Equations. In previous classes, we have studied more about ordinary differential equations and partial differential equations. But today we will discuss about the applications of differential equations. Actually, in engineering side, especially in electric engineering, chemical engineering, then uh, uh, different kinds of sector we have to use these differential equations and even robotics, then in various applications of electric circuits, especially in partial differential wave equation, uh, uh, heat equation, Schrodinger. We introduced it in your previous class, just previous class, partial differential equations. uh, Now today we'll start with the applications of differential equations for only ordinary differential equations. So in previous applications to differential equations, uh, in this chapter we'll study the application of differential equations to various physical problem and electrical circuit. As an engineering students, you must know about these circuits. Uh, we will consider the circuit made up of voltage source, which may be battery or generator, voltage source, resistance, inductance, and capacitance. There will be two parts. And designing with this, there are seven elements to combine the circuit. This is the symbol and this is the unit. You must know about this: charge, current, resistance, inductance, capacitance, electromotive force or EMF, or voltage, same words, variable voltage. Okay, all this is the unit. And the formation of differential equation for an electric circuit depends on the following laws. This is the actually electric current I equals to rate of change of charge with respect to time. Okay, dq by dt. And the voltage drop across the resistance R equals to Ri, and voltage drop across the inductance. This is the formula for voltage drop across the inductance, L into di dt, and voltage drop across the capacitance, Q by C. So using Kirchhoff's law, we voltage law, current law, and LR circuits, we can form this differential equation actually. Ri plus L di dt equals to E, total EMF. Okay, this is the actually voltage law using Kirchhoff's law and current law. So you can write this differential equation uh, by dividing L on both sides. Okay, di dt plus R by L I equals to E divided by L. This is the actually linear differential equations. We have solved linear differential equations in our previous classes. Linear differential equations, you have to this is the dy dt type, dt plus p y equals to q. Here equals to p equals to what? R by L. That means the integrating factor will be e to the power integration p dt. Here t is the independent variable and I is the dependent variable. So single independent and single dependent, so it is ordinary differential equation of first order, first first derivatives only present. So integrating factor will be e to the power p dt, and e to the power integration with respect to time t will be only t. Okay, its solution will be what? Dependent variable into integrating factor equals to integration of right hand side into integrating factor. Then there will be a constant a, integral constant, I into e to the power r by lt equals to e divided by l is the constant, and e to the power x formula e to the power x, but we have to divide with the coefficient of t. Coefficient of t what? R by L. Coefficient R by L, dividing by R by L we get L by R. Okay, after inverting, this is the integral constants. then dividing with this e to the power r by lt, we get this one. This L will be cancelled. Then at last electric current will be this. This is the actually general solution for the differential equation, first order fundamental. And this is our circuit. Uh, so at time t equals to 0, no electricity will be passed. Okay. At time t equals to 0, there will be no electricity. I equals to will be 0. So putting t equals to 0 and I equals to 0 here in equation 2. So this 0 and a into e to the power 0 means what? 1. E to the power 0 means 1. So a equals to what will be? Minus e by r. Okay. A equals to minus e by r. So in x-axis t and in y-axis e divided by r. Understand? So at time t equals to 0, I equals to also 0. I means what? Y-axis. This is the dependent variable and this is the independent variable. So at initial conditions, I equals it at t equals to 0, I will be 0. Then putting these values, we get the integral constant value. Then this will becomes a particular solution. And another example, another example, an inductance of 2 Henrys and a resistance of 20 ohms are connected in series with an EMF volts, E volts. EMF will be E volts. If the current is 0 when t equals to 0, find the current at the end of 0.01 second if equals to 100 volts. The differential equation of the above circuit can be designed. Actually, there are L equals to what? 2 Henrys. It is given, and capital R is the resistance, and E is the EMF, which values 100 volts. This is given. And within this circuit, you must know about the differential equation L di dt. Total EMF what will be? L di dt plus Ri equals to E. Then dividing with the same as before example, dividing with L, we get this linear differential equation of first order. So linear differential equation of first order, for this integrating factor will be what? E to the power p. P means what? Coefficient of dependent variable. Okay, p dt. T is the independent variable here. So after integration with respect to t, only r by l is the constant. So t e to the power r by l into t. Now its solution will be just this as previous example. So putting t equals to 0, I equals to 0, we get I equals to what? A equals to minus e by r. So putting the values of A, we get the electricity what? This one. Dividing with this on both sides. This will be cancelled, and here e to the power minus after division. So total electric current will be this. On putting ERL values, we have given these values. Okay, L equals to 2, equals to 100, R equals to what? 20 ohms, and time equals to what? 0.01 second. So after putting these all values, we get approximately electric current is this ampere. Okay. Now solve another example. Solve the differential equation L di dt plus Ri equals to E naught sine omega t. Actually, this is the differential equation of first order, where L, R, E naught are the constants, and discuss case when t increases indefinitely. Okay, this is the given condition, t increases indefinitely. In this circuit, EMF what? EMF capital E equals to E naught sine omega t. Okay, and Ri, this is the electric current, and R is the ohm, L is the electric conductance. Okay, so electricity will pass from positive side. Now solution, this is the given differential equation of circuit, and we can write this one by dividing L on both sides, dividing with L on both sides. So this is also linear differential equation of first order. So integrating factor will be what? E to the power integration p dt. P means what? Coefficient of dependent variable. Dependent variable what here? I. In replace of y, I present, and in replace of x, t present. So t is the independent variable. So after integration, same integrating factor we get as the previous example. So the solution will be what? Dependent variable into integrating factor equal to integration of right hand side into integrating factor. Okay, this is the right hand side, and this is the constant, and this is the integral constant. Now e to the power x sine bx, e to the power x sine bx formula. You must know about this from integration. E to the power x into sine bx formula will be e to the power x divided by a square plus b square sine bx minus tan inverse b by a. Okay, this is the integration formula. We have to use this formula here. So a means what? R by L, and b means what? Omega t. Okay, so after putting this formula, E naught by R is the constant here. Then the formula began here from here. E to the power x, a means what? R by L, square root over R by L whole square, omega whole square. Okay, sine bx1, b means what? Omega. B means what? Omega. B, omega t minus tan inverse. B means what? Omega. A means what? R by L, and it will be L by R. Okay, L by R, because this is the divided by A, so it will be inverted. Plus A, this is the integral constants. So I equals to what will be? We have to divide with this. Okay, after dividing with this will be cancelled. So only E naught divided by R square L square omega square sine this. A into what will be? E to the power minus this, because after dividing. Now as t increases indefinitely means what? T increases indefinitely means what? T T what? T will increases infinitely. That means if T T tends to infinity, then this whole term will be tends to zero. Understand? If T tends to infinity, that means e to the power minus infinity. That means what? 1 by e to the power infinity. 1 by e to the power infinity means what? 0. So this whole term will become 0. Understand?